In this problem, we see that there are two currents. One is a line current carrying a current of I1 amperes, and the other one is a loop of current that's like I2, right? So now both the current directions are given, and the coordinate axis is also given, right? So we'll use this as our reference. So that means I1 is flowing through in the positive y direction, right? Because it's going upwards, and according to this x and y direction, it indicates that it's going in the positive y direction. The current values are given, and the dimension of the loop is given. So the width is 2 meters, and the distance between the wire and the loop is 3 meters, right? And the height of the loop is 4 meters. Now, in the first part, they have asked you to find out write the magnetic field expression with function of distance, right? So that's like for current I1. So we know that for current I1, it's just according to the convention. If we apply the right hand grip rule, right, the magnetic field direction is pointing like this. And for this one is just simple and straightforward. So basically for part A, that's like the magnetic field is given by mu naught I1 divided by 2 pi r, and remember to keep since it's a vectorial component, so give an r, so this indicates that the direction of the magnetic field is according to this convention, right? All right, that's like part A. That's like simple and straightforward. So for part B, they have asked you to find out the forces on sides A, B, and CD, right, of the rectangular wire loop because of a magnetic field due to I1. Now remember that we know that if the force between two current carrying wires is given by mu naught I1 and I2 divided by 2 pi r, right? So r is the distance between the two wires, right? Now, in this case, you see that for this to happen, this formula gives you Newton per meter, right? Because this is giving me how much force that's acting on the wire per meter. Now, remember, we have to take the dimensions. So the force, let's say if we see sides AB, was the force on side AB, right? So that's the force for this side. So for this side, we see that current I1 is flowing upwards, right? So that's I1, and also the sides A and B, uh, the I2 is also flowing upwards, right? So in this case, the direction of the force on I2 on the side AB is gonna be like this, right? So the force on the side AB is on the left, right? And according to our sign convention here, we know the left means minus x, right? So our force will be negatively termed in this case, right? And what's the dimension of our AB, right? The AB is equal to the length of AB is h, right? So that means per meter, I have this much force, right? So what's the total force? So per meter times the length, which is the height, right? So now what's going to be my FAB, right? So that's just basically minus mu naught I1, I2 times 2 pi x1, because the distance between the two wires is x1, right? Which is equal to 3 meters. So it's like 2 pi x1 times h, right? So if you just plug in the values, you'll get that FAB is equal to minus 4 micronewton, right? And also like it's in the x-axis direction, right? Because it's in the minus x-axis direction, right? So since it's a vectorial component, I just put this extra x-axis direction. Now, was the force on the side CD? Now let's say for the side CD, right? For the side CD. Now for the side CD, remember my I1 is going upwards, but for the CD, let's say for the CD, the current, because the current is flowing in the clockwise direction, so for CD, the current has to go downward direction, right? So I2 is going downward for CD with the same length as H, right? So therefore, since the current directions are opposite, I will have forces acting like this, right? So you see the force on the side CD, right? It's on the right hand direction, which is in the positive x-axis direction, right? So therefore my force will be positive in this case, right? And the same, everything will be same as before, right? So what's gonna be my FCD? It's gonna be positive mu naught I1 I2, right? Times 2 pi r, right? So r is the distance between the two wires. In this case, it's between I1 and CD, right? So this is basically x1 plus the width, right? The width of the coil. So it's x1 plus the width of the coil, right? So that's like 3 plus 2 meters times h, right? So once you plug in the values, you'll get positive 2.4 micronewton, and also like vectorially in the x-axis direction, right? So that's your FCD. Now for part C, they are asking like if the rectangular while loop is suspended and free to move, which direction will it move, right? So basically, if your loop, right, if your loop is like free to move, let's say, in which direction will it move, right? So we know that for the side AB, right, for the side AB, there is a negative direction force, right, which is equal to like in the left hand direction, so which is equal to basically 4 micronewton, right? And also for CD, there's a right hand force which is 2.4 micronewton, right? So you see on net there is more force on the left, right? So therefore the loop will move to the left, or basically in the negative x-axis direction. All right. Now for the last part, part D, right? For part D, here they have asked like what's the magnitude of the magnetic flux passing through the rectangular wire loop due to current I1, right? So you have to find out the flux going through the loop area, right? Going through this internal area, right? The completely internal area. Now we know that our flux phi B, right? It's basically B dot dA, right? Now remember that for our loop in this case, right? So in this case, uh, this dA, right? So it's dA is basically, let's say, let's consider that you have a line, right, of length h, which is the height of this loop, right? And then you move a distance, let's say dx1 in the positive x-axis direction, right? So then basically you have an area of h time dx1, right? So now what's gonna be your limit? Your limit's gonna be x1 to x1 plus w, right? So basically your limit's gonna be from, you're starting from x1 till you go to x1 plus w, right? So now this is the area that you're looking for, right? So that's your dA, right? So this is your dA. So what's your dA? It's h times dx1. All right. So now let's see our phi B. What's this gonna be? It's the magnetic field, right? This one is because of the current I1. So that's like mu naught I1 divided by 2 pi r, right? So this is the r that's starting from x1, and we have to integrate it from x1 till x1 plus w, right? So this is the integral limit, and this is h dx1, right? So this is basically, I can, yeah, so I can just write this as my dr, right? Since this is, I'm considering this as the r direction, which is equal to the x1 direction, right? So I can just consider this as dr. Okay, so now if I do the integral, so that's like mu naught I1 divided by 2 pi h, right? That's like 1 by r dr. Okay, so now I'll just take everything, all the constants out. So I'll just take all the constants out. So then I will have basically 1 by r dr, right? So 1 by integral of 1 by r will give me ln, right? So basically I'll have h, this is h, 2 by ln of, let's say, r. And what's going to be my integral limit starting from x1 to x1 plus w. So that's my phi b. What's the unit? It's Weber, right?